Recording has started. Hi everyone, Quantum Computing Gates and Circuit Part 2. Gokhale is on the session 10. Go ahead, Gokhale. Take over. Gokhale, could you hear? Can you start?
I'm already on. Am I audible?
You are audible, but your screen is showing people only.
Yeah,
Can
it
you
might
switch
take a
to?
minute. I've already
Okay.
switched to this.
Yeah, okay.
Yeah, can you see the screen?
Yes.
Yeah, okay. There must be a small delay here, so please bear with me. Very good morning, good afternoon, good evening, wherever you are. I'm Gokhale Jayanti. I'm signing in from Mumbai. And today I'll just take you over through how to use IBM Qiskit in getting started with writing some small quantum programs, essentially to set up some quantum circuits using the so-called familiar gates. So we will try to understand this behavior, and this is basically once again a starter session so that you are familiar with how to use the Qiskit. And we are going to use this Qiskit throughout the remaining sessions of the course in most of our understanding of the concepts, right? So with what I have for today, we are actually on session 7 to 11. Basically, we're looking at quantum circuits. And once this topic gets over, we are going to move over to quantum algorithm, more specifically the communication algorithms and the computer algorithms. I will just get started with how to use this IBM Qiskit. And today, as part of a small theoretical session, I will also like to discuss this Walsh-Hadamard gate. It's a nice gate, and the reason why we discuss this very specifically is because of the fact that this Walsh-Hadamard gate does not have an equivalence in your conventional gates, right? So far, what we have studied, the conventional gates also have got an equivalent quantum gate and vice versa. Whereas the moment you talk about this Hadamard gate, or more specifically the Walsh-Hadamard gate, there is no equivalence in your conventional binary mechanisms or conventional gate operations. We have already seen the Hadamard gate in the sense that it is that very simple gate that picks up maybe any qubit state and puts it into a superposition state, and that is one of the fundamental usage of the Hadamard gate. So we will quickly also look at the properties of the Hadamard gate, and we'll also look at the core concepts of the rotations, right? But I think I'll come down to this theoretical part after I complete that small exercise on using IBM Qiskit. So let me directly jump over into using IBM Qiskit, and then I'll come back to this particular topic. Okay. So I hope my screen is visible. So all I need to do once again is, remember last time we were using the IBM Composer, and using the IBM Composer, you can actually create your own circuits, right? You can use the GUI, drag drop, and then build your circuit. So IBM Composer is a GUI tool which allows you to build your circuit. So what I will do is I'll show you the other way around. Also, you can just write your circuits, develop them using the Qiskit library provided to you through Python. So let me log into my account. Okay, so I just type in my ID. Okay, so okay, I've signed in. And the moment I sign in, as we have seen last time, yeah, just a minute.
Gokhale, while you're getting in,
Yeah, go ahead.
yeah, just to reiterate that we have covered most of the gates earlier in session 8 and 9. If you think you have not seen the gate, please refer to that. Plus, the recommended way of going through the
Prakashi,
book.
your echo, Prakashi is echoing and going bad. Your voice is echoing. You have two devices.
Okay, Gokhale, go ahead.
Okay, fine. Am I audible, Dhaval?
Yes, you are clear. There's no echo when you are speaking.
Okay, fine. Yeah. So we'll come back to that. We'll come back to what Prakash was trying to say. So I've just logged in into my account, and I hope, and at least by this time, I believe that you people have created your own account, right? A pretty very simple to create your account. We have seen that also. And remember, we had this IBM Quantum Composer, what we have seen last time. And let me just quickly launch that. And the moment you launch that, whatever circuits which we were building will come back once again to life, and then we can execute that. We have seen this last time. Okay. So instead of using this IBM Composer, we can also now use the IBM Quantum Lab. Now, what does this Quantum Lab provide to us? It provides to us a Jupyter notebook. Please, once again, remember this Jupyter notebook is not the so-called normal Jupyter notebook which you get through Anaconda. Here, the Jupyter notebook is sort of pre-configured to work in context with the IBM Qiskit libraries. So the best part about this Jupyter notebook is it is right already coming with all the nuts and bolts pre-installed, right? So all the goodies are pre-installed. So you just the moment you open up your uh, Quantum Lab, automatically it opens up your project workspace, and from the project workspace you can launch maybe any notebook, and this notebook is very much similar to the Jupyter notebook only, excepting for the fact that this is called as IBM's Jupyter notebook. So you have got different types of notebooks which you can create to begin with. You know, you get also some form of notebooks which are there to get yourself started. You can try out with that as well. And if you look at my left hand side pane, all these are all the notebooks which are already there, probably which I have been working on, and these are the gates which or these are my projects which I'm using. So all of them are once again the Pi notebooks only, the interactive Pi notebooks only. Okay, very simple. You can also create your own notebook. For example, you can just go down to saying file or click out over here and then just say Python 3 notebook is what you're going to create, and then you get started. So this is your notebook which is already there now. And I told you it gets started directly, gives you some sort of a uh, uh, some sort of a mechanism wherein you can directly get started with writing your primary code. Okay, so this is the support which is offered by the IBM. Let us say the Quantum Lab, as we call it. Right. Right now, I will not be using this particular part. So let me go back to terminating this. Okay, I just discard this, and what I can now do is something like this. I just open up a notebook which I have already created, because that saves a lot of time in terms of typing out the statements, and we can do a little more in that, right? So what I will like to do is something like this. I will typically take this testing gates the notebook which I've created, and this the objective is to just set up some sort of a notebook which goes through understanding the behavior. You can also see some visualizations of these gates, how they work before applying a gate to a quantum system and after applying the gate to a quantum system. So you can see that that is how I just wrote some very elementary notebook case out over here. So basically, this is from a learning point of view. And secondly, quite a good number of these examples are sourced out from even public domain examples. The reason being, you know, at least you will not be lost in understanding or identifying things more about these particular gates, right? So these details are also available in a quite a good number of public domain and listed out examples, right? We are not really doing some application of our own. We are going to do that and target that for a later date. So let me get started. I'll just select this, and then I will double click, and the moment I do that, I'm opening up my notebook, and this notebook is called as testing gates INPB. Remember, using this, you need to have some reasonable good understanding of Python, number one, and number two, you basically it's all Python coding, right? And you're going to use the entire IBM Qiskit library that is provided to you. More specifically, the Python module is available to you, and you don't have to pip install all of this. Remember, if at all you have to work on, let's say, your normal uh, uh, Google Colab. Okay, I'll just show that to you also in a minute. Okay, so where was that? Yeah. For example, last time, if at all you would like to set up something, this is your Google Colab. If you're working in Google Colab, this also gives you a notebook, right? And out over here you have to do all of that all by yourself. The best part is you have to set up your entire system. You have to install Qiskit, you have to install the runtime for that, you get your token available to you, set up the token, and then you have to just get started and prepare yourself before you can actually start writing your application code, right? So this is also one way to do this, right? I'm not saying this is not the way, or it's similar thing also can be done through maybe Spider or any other notebook or any other type of an IDE, right? So the reason why we have chosen is the moment we switch over to, let us say, our the notebook which is supported out over here, this comes pre-installed. You don't have to set up and install anything else. So that is the reason why we prefer to use the IBM's Jupyter notebook, right? Remember, the behavior working is all absolutely quite similar to your standard Jupyter notebook, which is available on Anaconda. So let us go through cell by cell. We'll just see how and what we are going to do as part of this small training. It will take about 1 hour. Kindly bear with me. And first and foremost thing is I need to have a whole bunch of modules and packages imported, right? As a standard Python requirement, you have to import whatever modules you are going to use. So the important things which I'm requiring to use will be discussed out over here. So I just start saying that from Qiskit import quantum circuit, execute, air, and IBMQ. Now, what are all these? Quantum circuit enables me to set up my quantum circuit, create the interconnection patterns, and add gates to that quantum circuit. So that is all made available here. Execute allows me to run my circuit on a particular backend. Now, the backend could be either a physical backend or it could be a simulated backend. So, but the execute is the one which is actually responsible to identify whatever is the currently established connectivity to a backend and downloads your code to be executed on the backend. More about that execution mechanism, we are going to talk about it in the uh, next session when we talk about what is meant by transpilation. Air is a mechanism wherein it offers you a whole variety of simulating environments. So we will talk about that air also in a little more detail. But as of today, we will just assume that air is available to us, which provides to you a simulator, and then directly I can just pick it up and then do my simulations. And IBMQ gives me an actual access to the real backend. And it also not only just does that, it can also allow me to do these operations in a simulated manner on my cloud, or it also allows me to hook up onto the physical device. So IBMQ is that. See, here is the case. I just IBM Qiskit compiler. So I'm just using this Qiskit compiler, and I just import transpile and assemble. Now, transpile and assemble are the two operations wherein whatever is a circuit which you have created out over here, it will be analyzed and it will prepare an equivalent representation on the associated backend. If at all I have associated my program to be executed on a simulator, then it will just try to represent this circuit or my project in the form of what can be executed on the backend. Whereas, if at all I've chosen to use, let's say, a very specific device, right? Let's say I'm using a device in IBM Perth, right? So that is one of the available instance to me. Then this transpilation will convert my project code into something which can be ported onto that particular IBM Perth instance, right? So all that is typically what the transpilation and the assembly will do. So once again, we will talk about this a little later stage. Then, I require all the tools supported for Jupyter, and whatever I want to visualize in the form of a blotch plot or a Q plot or a histogram, etc. I will use a bunch of visualization tools, and for that I will require this import Qiskit visualization import star. More specifically, if at all you want to go over into visualizations, I have just specifically mentioned out over here. You can just get a plot of the state in the form of a Q sphere, or you can just create a plot as a blotch plot, or you can also plot this as a block vector. So the block vector or the multi-vector, as we call it, can be plotted using these additional visualization features, right? So for that, obviously we require to import these specific packages. Okay, so what I will do is these packages have to be imported before I can proceed to execute any other cell. So let me quickly select this cell. Shift enter will cause that to be executed. So this is the first cell that got executed out over here. So now all the imports are in place. If there were some issue out there, they would have got an error message down there. Next thing, what I'm going to do is I'm going to create a quantum circuit. Remember, the quantum circuit will be created out of some bunch of a combination of quantum register and a classical register. We have seen that also. So I can define what exactly is the typical structure of my quantum circuit. So I will specifically create maybe a 2-bit quantum register and an associated 2-bit classical register. So with 2-bit quantum registers, I will get 2 quantum bits, and I can typically have got 2 raised to the power of 2, that is 4 different states, that is a 0, 0, 0, 1, 1, 0, 1, 1. And I can just write my program which will manipulate, which will operate on these particular quantum states. And ultimately, whenever I do a measurements, the state of this quantum circuit will collapse, will be captured into the classical register. So that is the reason why I define this. So it is also called a 2x2 circuit, right? 2 quantum register bits and 2 classical register bits.
Gokhleji, one
Yeah.
quick one.
Yes, sir.
I don't know the others, but the font is very small. So is
Let
there
me
a way?
see. Yeah, I can just let me just check out. Yeah, is this helping out, Dhaval?
This is better. Font is not limited, but the clarity is not there of the character.
Uh,
How is
uh,
it for others? Anybody comment? Now it's at least you can. I can make out now.
yeah, you can make out. Yeah, I'll share this notebook. Right, the entire notebook I'm going to share it to you, so you can just play around with that too. Right. So kindly bear with me. And these are some issues which we need to face, because I'm right now operating from Mumbai, and we still have a bad weather here in Mumbai. Okay.
It's okay now.
Yeah. Thank you, Dhaval. Okay, so this is where I just create my quantum, let's say my entire complete system, which is comprising of 2 bits in a quantum register and 2 bits in a classical register. So there are 2 qubits and 2 classical bits, right? So let me create that. So I just run this cell, and the moment I run the cell has got executed. And what happens is, the moment the circuit is created, right, as a standard feature, both the qubits, or maybe if at all you define a circuit over 10 qubits, all these qubits will be initialized to the basic state of ket 0. So that is all the inputs will be forced to be in the ket 0 state. That is also called as a reset state. So that is startup state, right? So I just made a comment out there. Now what I will do is something like this. Before we actually perform some operations, there are some methods which are available to interrogate and extract some properties of this particular quantum circuit. Okay, so what are these particular methods? Remember, to create a quantum circuit, I now execute this. I just say QC1 equals to quantum circuit Q comma C. And what is that Q and C? Q and C are already defined out over here. Q is the quantum register and C is the classical register. So using this quantum register and the classical register, I'm now creating the quantum circuit out over here in the next cell. And having created the quantum circuit, right? Some people also write it as QC equals to quantum circuit within bracket 3 comma 3. So basically you are creating a 3 by 3 or 3 cross 3 type of a circuit. So 3 quantum bits, qubits, and 3 classical bits, the conventional bits, right? So you can either specify that way. I just prefer to put them through the specifically the variables. So having created that, what I'm going to do is I'm just going to check out a few properties. So what are the properties? I can take QC1, display the number of qubits. So that is very simple. So QC1 now becomes a quantum circuit object, and then there are a whole bunch of methods which allow me to extract some properties of this particular quantum circuit. So one first property is qubits. So that will tell you the number of qubits. CL bits, classical bits. So number of classical bits, right? So this also will typically give me another way by which I can actually display the number of qubits. Similarly, the classical bits. So there are slightly different ways of looking at both these two. So the information that is provided to you will be slightly different. Here you get the complete information about the register, whereas out over here you just only get a numerical representation as to how many classical bits and how many quantum bits are there. Then you have got a method called as width. So width will tell you how many number of lines are there. Remember, in our circuit there are two quantum lines and two classical lines. So totally the width is essentially 4. So that will be the 4. So that is the width of your circuit. Then the size of the circuit. So the size of the circuit typically tells you how many number of total gates you have added your circuit typically currently has. Right now our circuit does not have any gates that are added. So you should be getting a value equal to 0. And the depth typically tells you, if at all you keep on adding the gates, right? So for on quantum line number 1, let us say you have 4 gates. On quantum line number 2, you have got about 6 gates. So the depth typically tells you the highest number of gates which are already applied onto any of the quantum circuit line. And you can just display the total data about the entire quantum circuit by using this QC dot data, right? So these are basically some methods which are available to quickly check out some properties of the circuit which I have created. So let me just run this, and then the moment I run that, you can just see the fact that my circuit is created. And when I look at QC1 qubits and CL bits, it is just telling me the fact that these are the qubits coming out from the quantum register. They are labeled as Q0 and the Q1. So this is bit number 0 and bit number 1. And similarly, the classical register, you have got 2-bit register called bit number 0 and bit number 1, right? And when you look at num underscore qubits, you will just see the value equal to 2. These are the 2 qubits and 2 classical bits. And the width is about 4. There you have got 4 lines, right? And then you have got 0, which tells you whatever is the number of gates, which is the size, and depth is also 0 because I have not added anything. And the total data which is there in my quantum circuit is also null, right? I have not created any circuit, so there is no information which it can give it back to me in the context of the description or the operations which are getting performed in the quantum circuit, right? So just to show you the fact that these are the methods which are available directly, you can use it on your quantum circuit. So what I will do is, having created a quantum circuit, let us see how the circuit looks like on a block sphere, right? Remember, the block sphere basically is a visualization that allows you to look at or examine the state of a single qubit, right? And this is basically a state vector representation, whether the currently the state is at ket 0 or ket 1 or ket plus or ket minus, ket uh, I or ket minus I. These are the basic states. So it will allow you to identify where exactly is your current system. And if at all you have defined a system over 2 qubits, you will be seeing 2 separate block spheres, one for each of the qubit, right? So that is the block sphere. So how do I display the block sphere? So what I will do is, first and foremost thing is what I will have to extract the state of the system. So what do you mean by state of the system? There are, let's say, two qubits. So I need to identify what is the current state of the first qubit and what is the current state of the second qubit, right? So first qubit could be in, let's say, state 0, ket 0. Second could be in ket 1. Then I say that the current state of this system is 0, 1. Right? So I can estimate whatever is the state, and to get that I will use this import. I just say Qiskit.quantum info import state vector. So this state vector will evaluate what exactly is the current state of the circuit. So to do that, I will say state vector dot from instruction defined by QC1 extract the state, and that is stored in some variable called a state, and I can print it out. Remember, the moment I have extracted the state, that typically gives me what exactly are all the values, the state representation for my entire circuit. And what exactly is the convention currently? My circuit is a 2 cross 2 circuit, right? So with 2 qubits, I'll typically have got 4 possible basis states. So it will just display to me what exactly is the current state of each of the 4 possible basis states. So that is what my state will be. And then what I will do is, using the state information, I can now represent this state in the form of a block vector or block spheres. So to do that, I will say Qiskit visualization import plot underscore block multivector. This is multivector, typically it tells you the fact that you can plot multiple block spheres simultaneously, one for each of the qubit. All right, you have got variations for that, wherein you can just only display one vector. That's also very much possible. So you define one state and then that will be displayed to you. That is another variant there. But I'm using this multi-vector, and what I do is I just say plot underscore block multi-vector and then pass on the state. Where is that state? State is something which I got it out over here. And the moment I do that, it will display that. So let me run this code. Okay, so now you see this code got executed and it is currently showing me this particular state. So how do you read out this particular state? So currently, if you notice, this is at 0, qubit 0 is 0, qubit 1 is also at state 0. So this is a block sphere. Okay, so this is a block sphere. If a particular qubit is at state 0, you would see this arrow pointing upwards. If the current qubit will be at state 1, this arrow would be pointing downwards. Right? We have seen a similar sort of a thing even last time as well. So currently it indicates the fact that qubit 0 and qubit 1 are both at ket 0. So remember, ket 0 together will be 0, 0 state. At 0, 0 state happens to be the first state out of the 4 possible states. Remember, what are the 4 possible states? Ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1. So this is currently at the first possible state, ket 0, 0 state, and that is what is also shown out over here. Can you see that? So if you look at the state vector, it says the value is 1. Remember, the state representation values are always complex numbers. So you will always see the real part and an imaginary part. So the real part is 1, the imaginary part is 0. So this is as good as equal to 1. And the rest are all zeros. So it is 1, 0, 0, 0. So it is like a column vector. Remember, it is shown out over here as a row vector, but technically speaking, the state is denoted as a column vector. So what is the column vector value? 1, 0, 0, 0. And that 1, 0, 0, 0 indicates the fact that my system is in the basic startup state 0, 0. Okay, so remember, this is a very nice way to look at and probe into displaying the current state of your system at any particular point of time. So I'm going to use this pretty very often, so I don't have to explain this in future. So the moment I just put that plot block multi-vector and then run it, you can just see the system state at that particular point of time. Then what I do is I can also display the same block vector or block plot in a different context, in a different way. So for that, once again, remember, this is another way of getting the state. So I'll just say state equals to state vector QC1, a very simpler way. right? This is a simpler way, does the same thing. So here once again the state information is captured into the variable state, and then I can just say state dot draw, and I can just say output equals to block. Now this also gives me an opportunity to display the state in multiple different ways. So this is something like a wrapper function which is available to me to draw the state using different variants of a plot. So let me execute this. You should be seeing the same result out over here. Result will be absolutely the same. State is the same. I'm using the same circuit, QC1 only. And then I'm now generating a block plot. So this is another easier way out to visualize the details of your system. And the third way to visualize the details of the system is using what is called as a Q-sphere. Now, QSphere is something which is very specific to the Qiskit, and Qiskit tries to consolidate the entire states of your entire system onto one single sphere itself, and that sphere is called as a quantum sphere or the Q sphere. Now, what exactly is the Q sphere? I'll just explain to you in a minute. Give me a second. My goodness, I think this will vanish. Okay, I'll explain it here only. Give me a minute. Okay, what is this concept or idea behind this Q sphere? What IBM did is they have consolidated the entire system onto one single sphere. My drawing is very bad, right? And what they have done is this is my spherical representation. This is center, and they have identified different states or different points. So imagine this particular Q sphere is like a Earth globe. So this is your North Pole, and this is a South Pole here. Okay, and obviously this side will be your east and your west. This is your west. So imagine you have got a sphere, and then you have marked this North Pole, South Pole, east and the west. East and west might appear to be relative, but imagine that you're holding the sphere and not moving it, and then now the east and the west points are also now crisply defined. Right now, this is typically a four-way representation that allows you to define the state behavior of any 2-qubit system. Right, so for example, this can be identified as a state 00. Right, so this once again will be state 10. So this could be state 01. This is state 10. Now you must be asking, like, why did I not number these in a cyclic manner, right? There is a typical way. This is called as a Hamming way. In a Hamming way, if you just notice that adjacent state representations change only by 1 bit position. Now, for example, 00, from there, changing any 1 bit position, you can either get 10 or 01. Similarly, from 10, changing 1 bit position, you can come down either here or you can come down to, sorry, this has to be 11. I'm sorry, okay, 11. So this is how the state naming convention is done following the Hamming mechanism. Right, so this is for a let's say a 4-qubit system. So you can also talk about looking at this as a sphere, something like this. So this is your so-called equator line, and then you have these meridian lines. And the moment you have these meridian lines, you can now define the point here and the corresponding point on the back side, a point here and a corresponding point on the back side and the front side, right? Just imagine you have got these sort of lines there. So you can define those sort of points there. The moment you define those particular points, it allows you to now define 16 points. And 16 points typically allow you to define a 4-qubit system. Now you can also go ahead for a 5-qubit system, 32 points. 32 points will come up somewhere out over here. Right? Tropic of Capricorn, Tropic of Cancer, so something like that. Okay, so this is a very nice, convenient way to denote in one single sphere the state of your system. So this is something very specific, reasonably innovative in the context of the IBM's uh, Q state representation. Okay, we will see more of this as well. So coming back here, how do I display that? So what I will do is, once again, to display that, I will just have to import the appropriate visualization library for plotting the Q sphere state. So and once I do that, I will say plot state Q sphere, whatever is the state which I have extracted, directly I'll plot it onto the Q sphere, and this is what I would be getting. Right? Your quantum composer directly displays this to you at the bottom of the screen. You don't have to write any code, automatically it displays that to you. So now notice the fact that it displays that to you, and now you see this sphere, and current system is absolutely out over here, and it is now telling you the fact that the system is at state get 0 0, absolutely not 1. So what does this mean? There are two bits, both the bits are at 0 and 0 state. So that is your current state. Now the color out over here, when you see this blue dumbbell, that also is an indicator to what exactly is the phase. So you have got a phase color swatch here, and it tells you the fact that the current blue indicates the fact that the phase is at 0. Right? So this will be the magnitude, and then the color would typically tell you the phase. And second thing is what the dumbbell size also gives you an indication as to what is the actual value. Remember, these are unitary values, so this would be equal to 1. And in case the value is less than unitary, you will just see this dumbbell in smaller in size. Dumbbell is smaller in size. Just keep this in mind. So I have now displayed it also onto the this thing. So what I can do, I can also have got an alternate representation. I'm just getting used to the way different machine states can be represented on the block sphere. So I'm just taking some few examples here. So I can also display a block sphere using a vector representation of a state. So I can define the vector representation of a state, and using this plot block vector, that particular method, I can directly display that particular state as well. By chance, if at all you have done some computations and then you have got the current state of your system, it has been evaluated, and then if at all you have got a list representation of that, so here is a small example of a list representation, then you can typically use this mechanism to display that. So here is a very simple way. So I can now say bz equals to 0 comma 0 comma 1. So this is basically a vector that is a representation for, let's say, ket 0. Maybe, I do not know. So let us see what exactly, whether it is ket 0 or something else. Okay. So what I will do is, I just currently I'm just enabling that, and then I will just run this code. So you have got several things. I've just put all of them together out over here. So you can just uncomment each of the lines and then see for yourself how the representation looks like. Okay. So here I run this cell. What has happened? Bx is not defined. Where is my Bx? Oh, sorry, it has to be Bz. Okay, so that is my block sphere. Okay, so just notice the fact that I just have given a few examples of various values, and then accordingly, you see what does this basically mean? X is 0, y is 0, z equals to 1. So here, if you look at this block sphere, it is x equals to 0, y is equal to 0, z is equal to 1. It's a vector pointing to the north, right? That is equal to ket 0. So you can uncomment, let's say, let me just uncomment this, and I will comment this out just for your understanding. And I'm just putting this as x. So actually you need to make changes out over here in the comment. So whatever you put it out over here, that comes up as a small title for the visualization. So I just make that, and if I run this, you see this is a block sphere for bx along the x-axis. You will see that. Okay, so this is just to give you some understanding and some comfort level as to how to look at the block sphere for various basis states. Remember, these are all my basis states. ket 0, ket 1, ket plus, ket minus, ket I, ket minus I. So these are the basis states. So I just leave it at that. And you can also probably have a combination of these. So here is a small combination. So I have got some, let's say, a vector representation, which is something like np square root of 1 over 2, np square root of 1 over 2, comma 0. So what is that square root of 1 over 2? NP basically is the NumPy, the NumPy package which is available to us to perform these numerical operations, and I'm extracting the square root. So it is like square root of 2 comma square root of 2 comma 0. So that is the value, and I can display that. So let us execute this particular cell. See, I keep on forgetting that. So I just say import. Okay, so I'll quickly do that and then run that. And now you see NumPy is used, and then this is my block sphere. So remember, I've just put up some value for the x, value for the y, so which also means the fact that this particular vector will have to be in the xy plane, right? So it will be in the xy plane. So this is the vector in the xy plane, things like that. Okay. So this is a simple way by which you can familiarize yourself. Remember, we were also talking about the Hadamard gate, right? So I can just run the Hadamard gate also, but let me see if at all I want to run it right now or a little later on. Okay, so I can, yeah, I'll just run it out over here. Fine, here itself. So what I'm doing is, whenever I want to add any gate to the circuit, I have a very simple mechanism by which I pick up that circuit line bit and then perform a operation which will automatically add an element to that particular line. Remember, I've got QC1, that means for the quantum circuit 1. H stands for the gate, right? Remember, you have got various gates. Each of these is denoted by an operator, like H is for Hadamard, X is for, let us say, the NOT gate, CX is for conditional NOT gate, CCX is for Triffoli Gate, and so on and so forth. You have got variants, various representations for these gates. We will see how IBM Qiskit gives you that sort of a let's say, method representation for each of these operations. So here is a way by which I can add the Hadamard gate. And having added the Hadamard gate, I say that I'm adding the Hadamard gate on bit number 0. And what does the Hadamard gate do? Actually, it will do 2 rotations. Or when I talk about the overall behavior, the Hadamard gate is normally used to put a state into superposition. So here you talk about bit 0 being placed into a superposition state, number 1. And when I talk about this Hadamard gate as a rotation, it incorporates 2 rotations. One rotation on the z-axis, other one on the y-axis. So it will typically perform 2 rotations, one after the other. I will show you this Hadamard gate and the details in a subsequent slide later on. So once I perform that, and I can once again extract the state information, and then I can plot that. So the reason why I'm showing to you is something like this. I can display the state of the system before performing some operation. I carry out some operations on the different qubits, and then I can represent this after I perform the operation. So you can just see the state changes happen out over here as well. So here I just pick this up, execute, and now you can see the gate gets operative. And the moment I'm operating, what is happening? Only bit 0 is operated, and bit 0, when it is operated, you see earlier it was pointing to ket 1. Now it just gets down to pointing towards the x-axis, right? So just notice the fact that this is the state after the Hadamard gate has been applied. And now notice the fact that the Hadamard gate will put it into superposition. You can also see the state vector variables. It is now 0.707 for the first one, and it's 0.707 for the second one. And both of them typically indicate the fact that it is in ket 0 and ket 1, a superposition having a value of 1 over under root of 2. Remember, 1 over under root of 2 is 0.707. So that is how I can know it is in a superposition state, right? This is the two states for my first bit. Second bit here, both of them are zeros and zeros, 0 and a 0 here, right? So this is how you can typically represent the values in the state vector as well. Okay, so having seen that, I can also do the same thing, having applied the Hadamard gate one more time. What will happen? I take the gate, or I take a quantum system, apply a Hadamard gate, or if I take even a single qubit, apply the Hadamard gate. I apply the Hadamard gate one more time. It is like H dot H, right? Obviously, it will take the system back to its original state. So this is what I wanted to show here. So I'm just applying once again the Hadamard gate, and this will revert the system to the original state, and then I can display that. So let me quickly share that with you. And now you see the system once again. It was this way, right? I applied the Hadamard gate and it became this. Okay, and from here once again I apply the Hadamard gate, it comes back to the original state. Okay, you must be seeing a small deviation here. It is not exactly 0, but this value is e raised to the power of minus 17. That's a very negligible value. This is simply because of the small errors due to my computations. Okay, so this very quickly proves the fact that I can apply Hadamard gate in series, and then I can get the original state back out over here. Okay, so what I can typically do is I can also, remember, I have the state vector. Now this state vector I could probe exactly to find out the individual states as well. So for that, once having extracted the state, I can say state of 0 and state 1. Remember, the resultant of a state vector is just nothing but a dictionary of values. And this dictionary will be identified by the keys 0 and 1 and whatever, depending upon the number of qubits. So here I use that to extract the state value, and I can display that. So here S1 is there. I can just only display the S1 part. I don't have to display all the block sphere. I will just only display the block sphere pertaining to S1. So I can just extract that and then print it out also. Or I can probably even define it in this way and then also print it out. So I can do that here. Where is my ST? See, typing mistakes. Yeah. Yeah, so you can see that. So whatever is the state which I got, I am now displaying that for qubit 0. Okay, so having seen this, let us now carry out a bunch of measurements. Okay, so to do the measurements, I can create my circuit and then run the circuit. Now, how do I run the circuit? I require some infrastructure to run my circuit. You could either use a physical infrastructure or you can use a simulated environment. Now, once you want to use a simulated environment, you can use what is called a simulator that is provided to us, called as AIR, AER. So AIR simulator allows me to set up a circuit and then run it on the simulator. And AIR provides you a variety of simulators, right? Most popular of the simulator is the state vector simulator, which allows you to see how the states of your system are changing. So it will do the simulation at a state level. Or the other way is you can directly use the Quasm assembler. Now basically you convert this entire code into the QASM or Quasm assembler, and then that is what gets simulated. So you have got Quasm simulator also. Okay, so we will just show both of them very quickly. So first and foremost thing is what I can probably use a state vector simulator. So how do I typically do that? So these are the imports which are required. We have done that earlier, but putting into the context, I'm just showing you what are the imports required. So you just say from Qiskit import AIR, and then you also say from Qiskit import execute. Now this execute method is the one which actually takes up your code, the description of your circuit will be converted into a form and format which can be sent down to the underlying backend, right? And the backend would be instructed to execute this on the so-called backend related runtime. So here now the backend will have to be chosen. So what I can do is something like this. So I will set up a backend. So to set up the backend, I'll have to get a backend. So I can request AR to get me a backend, and this particular backend currently would be a state vector simulator backend. So I'm just preferring to use this backend at this particular point of time. So it's a state vector simulator backend. And once I got that backend, I will now execute the execute method. I'll run the execute method. So what is that execute method? I'm executing the QC1, the quantum circuit which I've created on the backend, and whatever is the result which I get, I'll just grab that using this result method, and then I will store that result into some variable, right? I've just chosen the variable name as result itself, and this is a common method technique used by Python programmers. We don't want to use too many variables. Secondly, this variable is self-explaining to the fact that, okay, this will contain the result, and I can now print out the result. So let us run this code here. Yeah, it has created already the result to me, and I can display the result here. Okay, so this is my result. So the result is coming from a backend called a state vector simulator. The backend version is blah blah blah. This has been submitted as a job, right? And it says that the job got executed successfully, and it has executed the result, and it has done this in one single shot. Now, what is this concept of a shot? Let's say you got some basic infrastructure onto which a quantum circuit is given up for execution. In a typical scenario, the circuit will be loaded onto a physical device, and there you allow it to execute for let's say 100,000 times or 10,000 times, and after that you typically identify the let's say the probabilistic behavior out of this 100,000 times. How many times did the circuit come down to state 00 or state 1 or state 2 or state 3 or whatever, right? That is how you normally do that, and you identify the what is the final state, typically plotting a histogram. Whereas when you use a typical state vector simulator, there you run it only once. Yeah. Okay. So here you just say that the number of shots, number of tries, or number of retries, or number of times you are executing your circuit is equal to 1. And it says that the measure is success, and then it just gives you measurement level is 2. You have measured 2 bits, and the data which is coming out over here is called the state vector, and now you see this value and a whole bunch of other things that is related to what is the CPU interconnection and blah blah blah. So this is the overall complete result. Out of this, remember, this is one part which is called the state vector, and then this is the state vector which you are interested in more specifically. So you can extract that out. So how do I extract that out? Right? You can just say get underscore state vector. Obviously, notice the fact that you can do this after the state vector has been computed, and that value can be stored in some other variable. So I've just stored this into a variable called as filer underscore state, and then I can display that. So this is one simple nice way by looking at only the state vector information extracted out of this entire outcome. Okay, so this is the description. This is my final state. Whatever it is, the final state currently will be 1 0 0 0, indicating the fact that the system is at state 0 0. Okay, so that is my state vector simulator. Remember, I told you there is also a quasar simulator. So let me show you what exactly we mean by the quasar simulator. So to understand the quasar simulator, and by the way, I told you AIR provides you with a support of multiple other simulators as well. We will slowly try to explore these simulators as we move forward in the course, a few of them. But you know, you can also look at the Qiskit, let's say the technical notes which are available. and you can get a complete detailed explanation about what are the different simulators and how they work, what exactly are the underlying noise models, and all of that can be checked it out also. So what I'm going to do is something like this. Once again, I just say from Qiskit import air and then also import execute. I've already done that, but as a small matter of practice, I just import that. First and foremost thing is what, even before I choose a backend, let me get a list of all the backends which are available. So I just say air.backends. At the moment I just use this backends, it is going to pull out all the backends which are currently integrated into air, and that list will be stored in the variable called as backends. And what I do, what I do is I just iterate over this list and print it out. So I just, for B in backends, I just print out B. So it keeps on displaying to me all a list of all the backends which are there. So I'll run this, and now you see these are all the backends which are supported. For example, air simulator state vector, air simulator density matrix, right? Air simulator unitary. We are going to use this unitary a little later on. Very nice way by which you can take any vector and then convert it into a unitary matrix. Quasm simulator. This is what we are interested in currently. Right? You have got a unitary simulator, a pulse simulator. Pulse simulator simulates the circuit as if you are triggering your circuit with a small microwave pulse. So you something like that is what is achieved using the pulse simulator. So I've got different types of backends available. So having identified these are the several backends, now you can decide which backend you want to use. So here I've chosen Quasm simulator, QASM simulator as a backend. So remember earlier on we had used the state vector simulator, correct? State vector simulator here. And now I just go a little more deeper to understand what are all the various simulators supported. And then I will pick up and then use this Quasm simulator. So I just choose this backend now. Remember, this is backend, this was backends. These are backends, right? So backends contain a list of all the backends that currently supported under air, and out of that I've chosen one backend. I'm sorry. So what is that particular backend? So the backend is get underscore backend, and then you choose the backend, Quasm simulator. So let me execute this. So currently now the backend that is selected happens to be the Quasm simulator. So what I will now do is this Quasm simulator is slightly different than the state vector simulator. State vector simulator runs your circuit only for one single shot and then extracts the state information, whereas the Quasm simulator allows you to simulate as if you are running the Quasm code on your device, but instead of the device it is basically trying to replicate a generic type of a device on your local system itself. So how do I do that? So I just say execute, that is a standard execute method, and then I specify QC1, the circuit which I want to simulate, backend, whatever is the backend which is chosen, and shots equals to 1024, that is the number of shots I want to run. Right? If you don't mention number of shots out over here, by default it just goes down to 1024. Probably you can just decrease this count or increase the count, that is up to you. And once again I will be getting the result which is stored in, instead of a variable name called as result, now I'm just storing it into a variable called as result Quasm. Okay, so it will just run this. Yeah, it got done. Okay, remember these are simulated environments, so it does not take much time, is that instantaneously executed. Now, having got the result, how do I know what exactly has happened? So this idea is something like this. I have got the QC1, my circuit. Incidentally, my circuit does not have any gates out there. And this circuit we simulated to run over 1024 times. And if it were a normal circuit, probably it would have come out in any one of the four states, either the state 00 or 01 or 10 or 11. And this outcome is what is stored in the result, and I can get the counts of these outcome. So I can get the counts to indicate how many times it was there in state 00, how many times in state 01, 10 and 11, and all of these can be plotted into a small histogram. So this is what is normally done just to see the overall behavior. But here you will just see a histogram where invariably you will see everything collapsing down only to a single state, right? And that also happens to be the state 0, 0 because I did not add up any other elements as well. Anyway, to set up the histogram, you say Qiskit.visualization import plot underscore histogram. Okay, so this is how you use the histogram, and then you just say final state counts result quasm dot get counts. Remember, this get counts method is very important. So I'm now getting the counts of all the final states from my circuit QC1 that is stored in my final state counts. So, and I can use this. Remember, now this will give me 4 different counts. Counts for state 0, 0, count for state 0, 1, count for state 1, 0, and count for state 1, 1. And all of that can be displayed and also plotted. So this is my way to plot. So I just say plot underscore histogram, final underscore state underscore counts, and then I choose the color of my plot. The color of the plot will be red, and I can give a small title. Title could be final qubit state. Okay, so don't expect any fancy histogram out over here. We did not add any circuit elements, so we will not be seeing much of the details, right? As we move forward, we will see a few more details as well. So let me first run this, and the moment I run this, what has happened? Okay, let me just move forward. I think I need to measure it. Okay, so let me just do the measure. Shall I do the measure here, or this guy is not working? Get counts QC1, quasm get counts QC1 final state. Okay, I'll just come down to this, right? But trust me, it will just typically work, and then actually you'll be seeing the histogram plotted out there. So now here comes the biggest question. I can display this on a simulated environment, or I can also use the real device. So this is what I wanted to show to you. So this is the crux of the entire issue. So remember, if at all I want to latch on to a physical device, a real device, obviously you need to have an account. That's why you are here. And the moment you have your account, you will be having one token that is distributed to you. So that is something like your API access key, which allows you to submit your jobs. Right? You can create a job, you can submit your job, the job will get into a queue, gets executed on the real device, and the results will be sent back to you. And the tokens which are available to us in the context of the account which I have created, it's a normal account, a free account. So that's the reason why it puts in a small restriction. So the token which I have allows me to set up not more than 5 jobs in the queue. Not more than 5 jobs in the queue. So that means what I can only maximum run up to 5 tasks submitted onto my real device at any particular point of time. So only after one of these completes, I can just load the queue with another job request. Okay, so that is a small limitation. If at all I were having a paid account, probably I would be getting access to more features, and I'll also be charged accordingly. Second thing which you need to note is this. If at all you are using a normal Jupyter notebook, you have to do this. You have to first set up your provider. And what do you mean by the provider? Provider is the backend infrastructure which provides you the infrastructure to execute your quantum circuit. Now that particular provider A, once again, quote unquote, could be a simulated environment, or it could be a real environment. So here I am now using a real environment, and I will just say provider equals to IBMQ dot load account. This is very, very important. Load account. So to use this, I have to import IBMQ. So from Qiskit, import IBMQ. The moment you just say IBMQ, now you are using a whole series of methods and classes that allow you to access the backend device. First and foremost thing I need to do is what? I just need to load my account. Now, what do you mean by loading the account? Remember, let me take you back to, sorry. When we were talking about this concept last time, remember we set up our IBM account and then we get an IBM API token. I told you you have to download the token. It's a long string, and that token acts as a key, the API key, right? And how do you set it up? First and foremost, you are going to do is like IBMQ.save account and then put up your API key. And the moment you do that, it is as good as saying the fact that you are now registering your key into your account, whatever is your account you have created, right? So now onwards, it is not your user ID password through which you're going to access the backend resource, but using this particular API key, you're going to access your backend resource. And then you are going to just say IBMQ.load account. So this will set up the connectivity, and then you also get to verify whether your account is up and running or not. Okay, this is what we have done some time back. So the same thing, I don't have to now do that save account because that account is already tagged and attached to the moment I log in. So the moment I log in into IBM Quantum, because I already have created my account, automatically the system will bind it to me. So that's the beauty of it. I don't have to do any save and all of that. Remember, if at all I were using Google Colab or even normal Jupyter or even Spider, I have to do this every time. Every time I have to set it up and then load my account. That's the binding I need to do every time. Here it is, binding is not needed. So I just load my account. So I just pick up the provider and let me just see what exactly is the provider I get. So the moment I have done that, it just tells me this is all there, right? Providers are also there. In case you want to use this, I can also use this provider IBMQ load account. It's already there. So I can just change this. There are some small modifications which are now suggested, some methods getting deprecated, but still it works out there. So there is a small warning out there. So don't worry about that at this particular point of time. Having got that one provider, incidentally, once again, IBM offers you multiple backends. So what is my account? My account is a free account. So under my free account category, which limits to me the use of a maximum of I think 7 qubits, there are multiple let's say physical devices which are available to me. I can access any one of them. So first and foremost thing is, let me check out what are all the backends which are available. And for that, I can run this method called as provider.backends. And this will list to me a list of all the backends available to me. So let me run that. Now you see, I've got all these backends available to me. So I've got a Quasm simulator. I've got one instance available at Lima, other one at Belem, Quito, right? Simulator for MPS, simulator for extended stabilizer, Jakarta, Manila, Lagos, Perth, and Nairobi. These are different places wherein I have access to simulators. Remember, these not exactly simulators. These are basically the actual devices, but these devices are the so-called free-to-use devices. So they would be having a restricted capacity, typically up to 7 qubits. Right, so I've got a whole variety. So you can now schedule your job to run on any of these backends. Let's say I can run it on Perth, or I can typically run it on Manila or wherever. Right, so you can choose your backend. But a better way could be something like this. Can I not discover which of these simulators is least loaded? Once I know the fact that okay, the queue size is smaller out there, then I can pick up that particular backend and then send my circuit for execution out there. Okay, so that might be a slightly better option. So how do I do that? So once again, I will do this from Qiskit providers IBMQ. import least busy. Now this is something which allows me to find out what is the least busy backend for a given criteria. So what is the criteria? Can you see this? I'm using this least busy function, and then I'm using a filter. I'm just filtering out all the backends which match this criteria. What is the criteria? So just the filtering is typically done by filters equals to lambda. So this is a lambda function in Python. Lambda function in Python is as good as writing a single line function. You don't have to really create a def, and you don't have to write a big contextual code. Here it's a single line of a code. So here you just say filters equals to lambda b. And what is that b? First and foremost thing is whatever is that current backend which is there, I just check out the configuration, and in that particular configuration I will just check out the number of qubits, and the number of qubits should be greater than or equal to 3. Okay, that is my criteria. And I will also say the configuration is not a simulator. I don't want to use a simulator. And third is the status is operational. Remember, status.operational equals to true. So that means what? The particular backend should be in a working state, operational state. So I just select all such, let's say, backends. And out of these, I will find out which is the least busy. So when I executed that sometime back, IBMQ Lima was the output. Let us see as of now, which is that. So it is running, checking out. It will take a minute. Yeah, it has come back once again, IBMQ Lima only. That is the least busy. So what I can do, I can, having gotten this information, I can just plug it in out over here. I can plug it in. So what I will do is I can now choose that particular backend. So how do I choose the backend? I will now say from Qiskit import IBMQ. I just get the IBMQ provider from the hub called as IBMQ, and the provider backend will be IBM underscore Lima, IBM underscore Perth, and so on and so forth. So if you say that no, I want to execute my code on a very specific backend, you identify the name of the backend here, right? So here I've taken this as IBM Perth. So, but here what I will do is, because I got IBM Q underscore Lima, let me dump it to Lima. Okay, so now I will choose IBM underscore Lima, IBM Q underscore Lima. Is it IBM Q underscore Lima? Yeah, let me try it out. IBM Q underscore Lima. I think it should be IBM Lima. Let me just see. Yeah, it's IBM Lima. Right? It's IBM Q Lima. Sorry, it's IBM Q Lima only. Okay, so I've just selected that. Let me just set it up. Yeah, it got through. So now my backend is chosen to be IBM Lima. And let me just confirm whether it is the same thing. Yeah, so it is IBMQ Lima is the backend which is currently chosen. And now I can set up my circuit. Okay, so what I will try to do is something like this. I'm now creating a totally different circuit. Now this particular circuit is QCA. Remember earlier it was QC1. I'm now defining another alternate circuit called as QCA, and this is a quantum circuit of size 2. What do you mean by that? There will be 2 qubits. So I will entangle both these two using some C0 gate. Remember the conditional NOT gate? The conditional NOT gate typically performs a NOT operation on 1 qubit provided the second qubit is equal to 1. Okay, provided the second qubit is equal to a 1. So if there is no activity for a certain period, automatically the quantum lab starts screaming. Okay. So here I'm defining that, and then I just say QCA dot x0 and x1. So what is happening? This x will do a inversion. Remember, x gate is applied, and the moment I apply the x gate, it is as good as converting the inputs from ket0 to ket1. So I'm making q0 and q1 equal to ket1, and then I'm also applying the Hadamard gate, the H. The Hadamard gate will convert line 1 into a superposition state, and then I add up this CX gate apply the CX gate, right? It should be the CX. Yeah, conditional NOT gate. And having done that, even before I run this, let us have a quick display. So how do I display that? I just say display whatever is a quantum circuit dot draw method, and the moment I do that, I'll get a typical display. So this is the display of my quantum circuit. Can you see that? I put up a X gate here, I put up a X gate, and on Q1 I have also added the Hadamard gate, and then I've put up this sort of the entanglement. Remember, the moment I put that Hadamard gate, Q1 is in superposition, and now with this entanglement, because Q0 is equal to initially 0, the inversion will make it equal to 1. Because of that, this conditional NOT gate would be triggered, and now you would be seeing at the output an inversion of the Hadamard gate, right? So Hadamard gate will have the two superposition states. The states will be inverted, right? So that is typically my circuit. And now this is what I'm going to typically run this, right? So what I will do is, even before I run it onto the backend, let me quickly see the simulation output here. Okay, so I will pick up a backend which is called as a state vector simulator. Remember, we did that earlier, and I will run my code QCA on that particular backend, extract the result, and then display the result, and put that also into my QSphere. So let me quickly do that. I do not know why this is not working, because it is not collapsed maybe. Okay, it is QCA. I keep on making these silly mistakes. Yeah, fine. Okay, so QCA, whatever is there now, it got simulated. Can you see that? Before, when I have the Hadamard gate, this value would have been here, and this would have been here. Now the fact that I've applied the NOT gate, it is inversed. Okay, so this would have been out there, this got inversed, and that is what you see the resultant after the circuit is applied. That's all fine. And now notice the fact that my system is in state 0, 1 or in state 1, 1. Why is it so? Because it is in a superposition state. So it is either in state 0, 1 or in state 1, 1. Why is it state 0, 1 or 1, 1? Because the Hadamard gate is applied to the second bit. Remember the second bit. So the second bit, first bit is definitely 1. The second bit could be either a 0 state or a 1 state. So that is the reason why you have got both these two states, state 0, 1 or 1, 1. Okay. So, hey Rama. Okay. So what is typically happening out over here is, because I'm applying the inverter or the NOT gate, one of the states will be inverted, right? It just goes to the inversion. Inversion means what? The coefficient now would be negative, and because of that, there is a flip in the phase, and that is what is shown by the color here. The color indicates the fact that this is in phase 0, this is in phase pi. Okay, so the phase is also shown in your QSphere. So now comes the actual aspect. Now what I am doing is something like this. Out over here, oh God, I will execute this one more time here so that my backend is there, because I want to use that backend, or else I'll be using the simulator backend, which is not right. So what I will now do is, I will now sort of submit this job out over here, right? So how do I submit the job? So I just put up what is called as a job monitor. The job monitor gives me all the features to manage my job queue. Now what is my job queue? The job queue essentially is a queue of all the jobs submitted by multiple users, right? Like you are submitting, there could be other users also submitting their jobs, And the job monitor will allow you to examine what is the current state of the queue. More specifically, it will also allow you to find out what exactly is the status of the job which you have actually submitted, right? The running status of your job, whether it is in a state of execution, whether it is just currently queued and waiting, or whether it got executed, whatever is the current status, that also would be displayed out over here. You can monitor that particular state. So how do I go ahead trying to do that? So I say from Qiskit tools monitor, import job monitor. And now I'll once again use the execute method. But this time I'm executing my circuit QCA on the backend. What is now the backend? The backend is the IBM Lima, which I've chosen. And I'm now running this for 1024 shots. So that is the number of shots which I've selected. And having done that, this job now would be transpiled and submitted. Now, please understand this. I have not specifically implemented the transpilation here and the assembly process here, but transpilation and assembly would be done automatically. So, what do you mean by transpilation? Your circuit QCA is there, and what is that QCA? The QCA is something like this, correct? This is my QCA. Now this circuit comprises of, let us say, 5 gates here. So here I've got about 4 gates, and these 4 gates have to be ordered in this particular manner. They have to be also triggered in this particular manner. So for all of that, whatever is the associated gates on the selected quantum computer, remember where did we select? We have selected IBM Lima. So on that particular backend, we really do not know how that is actually implemented, right? What are the actual underlying gates, how it is triggered? We do not really have an access. So that is all abstracted back to us. So what happens is this circuit definition is converted into something like a meta file that talks about the description of the circuit and submitted out there. And there is one guy somewhere who interprets this and then tries to do a configuration on IBM Lima which matches this particular description of your circuit. So that is what is called as transpilation and the assembly process, right? So I don't have to specifically do that. The moment I execute, that will automatically happen on the specified backend. Having gotten that, now I will just say job underscore monitor. So this job underscore monitor will now start monitoring the state of this particular job, and it reports to me what is the current status of the job. Now I can just see the current status displayed here. And if the job is terminated, it would have given me the actual job state vector from where I can get the counts. So how do I do that? I can just say job dot results dot get counts. Remember that. So the moment I do that, I get the actual counts, and those particular counts I can put it into some variable, and then I can display into a histogram. So I will just fire this query, and the moment I fire this query, this particular query will go for execution. Let us see. Yeah. So it says job is queued. Okay. So let us see where is the queue and all of that. What is the queue? What is exactly the status? I cannot really get any outcome. See, remember this cell is still under execution. Can you see the star here, indicating the fact that this particular cell is under execution? I really do not know how much time it is going to take. So let us get some simple guesstimate of that. So what I can do is I can just click on this option here on my left hand side menu. This will display to me list of all the jobs which are there. Right? Can you see these were the jobs which I submitted earlier on? This is a job which is currently submitted on August 8 at this particular time. So it is submitted on IBM Lima. I can just click on that to get more detailed information about this particular status. So it says it is created and it is in queue. Okay. So what I can also do is I can just get more details about the job status. Okay, so I can list all the jobs. Remember, these are all the jobs which are there. If you look at this job is something which is currently queued, and it says estimated wait time is about 1 hour. That's pretty good, and it says the fact that currently I'm in queue position number 10. Very, very good. When I've created, it is a queue position number 10, and from an instance point of view, I'm in queue position number 9. And as of now, the usage is still 0 seconds because my job is still not picked up for execution. This is a job which got completed. So let me just show that to you also. This was something which I fired about 8 days back, and it got also executed on IBMQ Lima, and it took about 2 seconds to execute. So let me select that and then display the overall status of that. This is, I'm displaying the status of a job which got actually executed, and if you see, this is my outcome, right? Whatever is the circuit, I just fired that. You can just see the quantum circuit. So this is some quantum circuit. I just did two types of the same thing, 3 bits, and then I got that as measured. Remember, the moment I create an empty circuit, all the inputs will be at state 0. So you expect this entire system to have an outcome of 0, 0, 0. Right. So what happened is, when I actually set it up, I will see the number of counts here. Out of 1996 times, it was outcome is 0, 0, 0, and then I've got small outcomes for 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, and the remaining are all definitely zeros. So you have the actual histogram after the circuit got executed. So this also tells you what exactly is the state while it was actually internally running on the quantum machine. Okay, so this is what I can just check out. Even our circuit also will typically land up into this sort of an outcome, right? So this is a more dumber type of an outcome, whereas our circuit today might be probably giving us a better resultant. Oh, it is still waiting. It is still executing. Current position is still number 10. We'd have nothing else to do excepting for waiting for that. Okay, so I will go back here. Let this wait, and then I just move forward. I'll not be using this circuit QCA. I'll be using some other circuits for my other explanations. Once this cell gets executed, we will start examining this periodically. Once this is executed, you will see the job status saying the fact that job is done. And once the job is done, I can execute this. The final state also counts will be coming out, and then I can plot the histogram. Currently, I cannot even plot the histogram. Okay, so as good as this, very much like you are running your normal simulator, here also now you can submit your job to the physical backend. Okay, so that is the main crux of the entire thing, how to do the mechanics, right? What exactly are the different gates, how do they work, that is something which is described out over here. So I think I will leave that for you to just work it out. So pretty very simple. Define a circuit, add the gate, view the system before, run the system, and after also you can just see the behavior. So here is a small example of defining a circuit, and then I'm just seeing the qubit 0 equals in a 0 state, the other two are in a 1 state, simply because I just have created that sort of a circuit here. Can you see that? 0 state, and I put 2 inverters, because of which the state is supposed to be in 0, 1, and 1. So that is my block part, and that also same thing is visualized in a Q sphere. See this, I told you these are now the states which are there on the Tropic of Capricorn and Tropic of Cancer. So you also have that states, and if I add a Hadamard gate to that, I can just see the difference out over here. So let me quickly execute, right? So what I'm doing is I'm defining another circuit called as QC2. It's a 3 by 3, it's a 3 quantum gate circuit. So I will execute this. What has happened? It is supposed to. Oh no, God! Till the time this is completed, I cannot move forward. Okay, I forgot that. Okay, so I will share this notebook. It is just exactly 8:30. I think I should not be delaying you. I'm going to share this notebook with you. What you kindly try to do is, please do not submit the job. Right? You have seen the submissions. I can show you the outcome of the submissions in the next session. Please do not submit, but after that, from here onwards, you can get started. So you can just execute starting from this particular cell. So then this will keep on executing, right? So you can just start executing. You can just see the behavior of all the cells. I have some outcomes also here. Some of the pictures are also there on same thing. I've just added X. How does the superposition work? These are all the rotations, a bunch of rotations. And then you can talk about the Bell state. Bell state once again puts you into superposition. That also is displayed. And then once you simulate that, remember that circuit, this histogram was supposed to come earlier on. It did not come. I do not know for what reason. So here is the histogram. Okay, so this is how the histogram typically comes. So here you are exactly having a wonderful distribution, 50-50 distribution, because it is the Bell state. And there's your control NOT gate. I'm having two inputs, and I'm defining a Hadamard gate on one of them, and then I'm also adding a control NOT gate later on. So this is my initial state. This is the initial state vector diagram representation. Then I add the control NOT gate. To add the control NOT gate, you just say CX. CX is the method call to add a control NOT gate. And the moment you do that, this is what you do as an entanglement. And once you do that and run it, this is the state vector representation. So it just does a inversion provided the input is equal to a 1. If the input is equal to 0, it does not carry out the inversion. And this is a swap gate. Okay, so swap gate once again is the same thing, right? I create one circuit, and the circuit initially contains a Hadamard gate, and then I display the state vector for the Hadamard gate. It is putting the Q0 into superposition, and then I put up a swap gate. This is what is my swap. So it will now swap both these two values. So the Hadamard gate values would be automatically swapped. So once it swaps, this is what you see as an outcome. Okay, so there is a state change that happens. So this is a swap gate. Remember, the swap gate will swap the gate states, the states. This is a Triffoli gate. This Triffoli gate is called as a CXX gate, and the Triffoli gate will be a 3 quantum gate. So that is the reason why I have defined this as 3 by 3. And what I do is I just add a Hadamard gate on one of them, and I set up my small state vector simulator for the backend, display that. So this is how it is initially. I just put up a Hadamard gate, and what I will do is Q0 and Q1, these two bits now will be the control bits, and my Q2 is a target bit. So the target would be this. So if at all Q0 and Q1 is both of them are 1, then only this flip happens on Q2. So for that purpose, what I will do is I'll add one NOT gate on Q0 and Q1. So that is the outcome. So I add a NOT gate on Q0 and Q1 here. Can you see that? And then I add the CCX gate. So the moment I add the CCX gate, this is what I get out over here. This is my circuit. Okay. So if at all you keep on executing the cell one more time, you will just see this getting added out there. So don't worry, internally, only from a visualization point of view, it keeps on adding that. So here I've added the CCX circuit, and the moment I've done that, I run it, and then I see inversion here. So that was the original, right? So this was the original. So you just see the entire thing getting inverted, flips to the opposite direction. Okay, so that is your CCX gate. Okay, so I'll share this notebook. Kindly spend some time, set up your own account, and then you can copy this entire notebook and then start executing. Coming back to the job which you have submitted, it is still in the queue. You can see that here onto the left hand side, it is still in the queue. Okay, so once it is done, then automatically it will display the status, and then it will also show me the result. So it will come up here. Just remember, this is the cell which is currently running, so job is still queued. Once it completes the execution, it will show the status change here, and then I can show this. So I'll just leave my notebook open, and I will wait for some time. I do not know, it might take 1 hour, it might take half an hour, 10 more minutes, or probably longer than 1 hour. So it's still in queue position number 10. Maybe someone must have fired a slightly longer job. It is taking more time. It says estimated wait is still equal to 1 hour. Okay, so that concludes my session. If there are any questions.
Yeah, just people have asked.
Yeah.
IPINB file.
Where is that?
It was in the chat window.
Yeah, I joined the session a bit late.
No problem. I have answered them. Simply we have to take a PDF of the session and put it.
Yeah.
And the IPINB file should be in the session 10 folder.
Sure, I'll do that. I'm just waiting for this the notebook to end, or else I'll be losing once again entire context.
No, I think what I'm going to do is I'm going to stop the recording.
Yeah, you stop the recording, please.